So why does the periodic table look the way that it does? Well, we can go back to the 100 years and more when Dmitry Mendeleev, for whom element 101 was named after, a Russian physicist chemist, decided to put all the elements that we now have in the periodic table that he knew about at that time into some kind of logical order or sequence. And so he, in a sense, took out a stack of note cards, wrote the name of each element on each note card and its relative mass and many of its properties. And he then organized that stack of cards from the element with the least mass, which would have been hydrogen, to those elements that had the greatest mass, of which he knew about, which would have been some of the transition metals. And then he would lay them out on the table, so to speak. And so he put down his first element, let's say hydrogen, and then he looked at the properties of the element with the next mass, helium, and saw that they didn't really match up. So he put helium beside it to its right. Actually, he did his from top down. In our periodic table, it goes from left to right. But let's put that difference aside for the minute. Then he looked at the third element, lithium, and noticed that it had properties similar to hydrogen. Now, today, we know why those properties are similar, because both hydrogen and lithium have one electron in their outer shell, which therefore means they're going to chemically combine with other elements in the same way. So he put lithium underneath hydrogen. Then he looked at the fourth element, beryllium, and beryllium did not have the properties of helium, so he shoved helium down a bit and made space for beryllium. And then he looked at the next element, boron and carbon and nitrogen and oxygen and fluorine, and none of these had very similar properties to helium, so he kept pushing helium farther and farther to the right. And again, he went downwards and we're going to the right. And then he got to neon and he saw that neon's properties were very similar to helium. Both helium and neon, he's noticed, were gases and were very inert. Then he looked at the next element, number 11, which was sodium, and saw that its properties were similar to lithium and hydrogen in the way in which it chemically combined with other elements. And so he put sodium underneath lithium. Then he looked at the next element, magnesium, which, lo and behold, had very similar properties to beryllium. And we know why. It has 2 electrons in its outer shell, like beryllium does. And so it combines with other elements, particularly the elements over here, in very much the same combinations, and so forth and so on. Now, this is a gross oversimplification of the process. The degree to which he even knew about the element helium at the time, I'm not sure. Because we discovered that on the sun before we ever found any of that on our own planet. In any case, that's how the periodic came to be. Now, interestingly enough, there were several elements, 31 and 32, right here, where, since they had not been discovered yet, he left those spaces blank. And then he got to arsenic over here, and then he got to selenium and bromine and so forth. But he left those 2 spaces blank. And that was a brilliant move on his part, because it proposed then, or it hypothesized, that these were spots where elements had yet to be discovered. After all, if we knew about these elements to the left of those spaces and these elements to the right, it's logical to think that there must be some elements that haven't been discovered yet. And when they were discovered, one was discovered in France, and the Latin word for France is Gaul. If you know anything about Caesar and his Gallic wars, Gallia est omnis tuissa in partes tres quorum unum inculant Belgae. All Gaul is divided into 3 parts. So during the Roman Empire, France was divided into 3 parts. So since it was discovered in France, they named it after the Latin word for France. And then the next element, germanium, guess where that was discovered? You are correct, Bolivia. No, it was discovered in Germany. So this is kind of how the periodic table came to be. And so the beautiful thing about the periodic table then is that all of these elements right here all have similar chemical properties, and we now know why. They all have 1 electron in their outer shell, and that outer shell is always the S shell. And then these elements all have 2 electrons in their outer shell, and these have 3 and 4 and 5 and 6 and 7, and then these all have an octet, except for helium, which only has 2, which means its outer shell, the first one, is filled up, and the other ones down here, their outermost S and P subshells are filled up with 8, which would be 2 plus 6, 2 in the S and 6 electrons in the 3 p orbitals, 2 electrons per orbital, for a total of 8 electrons, meaning that these elements don't like to gain or lose electrons because their S and P orbitals are filled, and so they are inert. This does not mean there are no compounds that can be made with them, but there are a few, though. Anyway, this is how the periodic table came to be developed. So, as we look at this table that you see here that is color-coded, this is very, very helpful. I would remember, if I were you, that the 2 rows on the left, the 2 vertical rows on the left, or we should call them columns, because the word row is used in chemistry for this direction, and column is used in this direction. The first 2 columns are called the S block elements, and they represent the alkali metals and the alkali earth metals, which will be mentioned in the next screencast, if I remember correctly. Then you have your P block over here. This P block represents the P subshell electrons. And you'll notice, of course, there is no such thing as 1p, because the first energy level only has 1 subshell, and that's the S. It doesn't even have a p subshell, so the first p subshell was called a 2p. Now, sometimes helium is put here, sometimes helium is put over here, because it does have 2 electrons in the outer shell, like beryllium and magnesium and calcium. It depends on the periodic table that you see and what the purpose of that periodic table in that particular chapter of a book might be. Then we have our D block down here, and you'll notice there's no such thing as a 2D or a 1D, because the first energy level and the second energy level don't have a D subshell at all. So the first D subshell we encountered is automatically called the 3D subshell. Now the F block right here actually goes up into there, as you'll see a little bit later, not up into here. It doesn't go up in there. It actually goes up right in here. And there are 14 there for the 7 electrons that can fit in the 14 electrons that can fit in the 7 orbitals, 2 per orbital. Remember, every orbital, whether it's an S, P, D, F, every orbital can only hold 2 electrons. The subshell can hold more than 2 because you have 3 orbitals in the P subshell, 5 in the D, and 7 in the F. So this picture of the periodic table is very, very helpful when it comes to using the off-bow principle to fill in, to determine the electron configuration of each of the different atoms. And the main value is that it helps us to predict the overlapping of subshells. So, for example, when we get to the 3s here, and then we go to the 3p, I'm going to erase some of the stuff here. When we get to the 3s right here, and then we move to the 3p right here, we say, okay, well, the next one, since we're talking about the third energy level, should be the 3d with its 5 orbitals. However, when we go to the next element after argon, this is argon right here, when we go to the next element, argon, we find it's actually over here. It is potassium. And so this tells us that before we get to the 3D, we are doing the 4S. And then we do the 3D, and the periodic table helps me to predict that the 4S is a little closer to the nucleus in terms of energy levels than the outermost part of the 3D, which is a little farther up on the energy scale. So the point we want to make here is, if you remember this sequence, the 1s, and then the 2s, and the 2p, and the 3s, and the 3p, and so forth, you are able to predict the order in which the subshells are filled and when there's an overlap. And again, by overlap, let me erase a lot of this stuff here. I don't know if there's a button to erase everything on the screen or not. I'm certainly not going to get all the marks off well, that got rid of a lot of this stuff anyway, just a little bit more. And a little bit more. So if you look at the periodic table, which you always have when you take a test or do your homework or a lab or something, and you need an electron configuration, which would be the arrangement or the organization of the electrons in their orbitals, in their subshells, in their main energy level for a given atom, this diagram is very, very helpful. Now, we've been using the diagram to help us to predict the way in which atoms the electrons of every different atom fill up their energy levels and orbitals. It also can go the other way around. We can take what we know about the elements and their properties, which are the result of their electrons, and we can use it to predict what this periodic table is going to look like. So the periodic table can serve as a guide in determining the order of filling of the atomic orbitals, which is the way we're going to use it most of the time. But originally, it went the other way around. We came up with the order that you see in this figure based upon the properties. So when we look at the electron configuration, you're going to notice several things. First of all, you're going to notice that across the top of the periodic table, there are only two elements, hydrogen and helium. And when we look at the electron configuration for helium, we have your first energy level, and the first energy level can only have one subshell, which we call the S subshell, an old-fashioned designation. If we were going to use the quantum number, we would call this the 0 subshell. Remember that? And then it has 2 electrons in it because it only has one orbital. The S subshell only has one orbital, and you can have 2 electrons in an orbital as long as they have opposite spins. And now we move to the second row across the periodic table that begins with lithium and goes all the way down to neon. And so now what we're going to do is we're going to take helium's configuration, which is this right here, and we're going to designate that with the brackets with HE for the symbol of helium. Don't be offended, ladies. And we're going to since those electrons are locked into the core, so to speak, we're just looking at the valence electrons when we do the rest of the configuration. And the valence electrons are going to be found in the second energy level, and there's only one electron to go because you've got a total of 3, and 2 of them are already spoken for in the core. So that third electron is going to go in the second energy level, and there's only one subshell. It's going to go in the second energy level. And that second energy level has 2 subshells. The first one is called the S subshell, and there are going to be 1 electron in it, and so it's a 2s1. This is, using the brackets of the previous inert gas, is a shortcut, and I would recommend you use the shortcut, because when electrons are gained or lost during bonding and during chemical reactions, it's never the core electrons represented by the inert gas in the brackets. It's always the valence electrons, which are the designations that come after the symbol in the brackets. Now, when we go across the second row, we end up down here with helium, right there. And now we have the second energy level filled, because in the second energy level, there are 2 subshells, S and P. All S subshells can hold a maximum of 2 electrons, and all P subshells with their 3 orbitals can therefore hold a maximum of 6 electrons. And then, since we filled up the second energy level, we now move to the third energy level, and we move to the third row on the periodic table, beginning with sodium. And so as we go across the table with sodium, we use the electron configuration of neon, put it in brackets. That's going to be understood. In other words, all of this stuff right here is now neon in brackets. And we're looking at the valence electrons after the core neon electrons. And so we're going to have 1 in the third energy level, which can hold 3 subshells. The first subshell is the S, and then 2. Now the S subshell is filled. Now we move to the third energy level, the second subshell in the third energy level, which is P, and 1, 2, 3, 4, 5, 6. And now we filled up the P subshell of the third energy level, and we're ready to start on the D subshell of the third energy level, which would be the third subshell. And the third energy level has 3 subshells. Remember that the orbitals, S orbitals, are always designated with the number 0 if you're going to use their official quantum number, and P subshells are always designated with the number 1 if you're going to use their official quantum number. Now, at this point, we see that if we're looking on the periodic table, the next element is potassium, and it's in the S block. And so right off the bat, we recognize the fact that because potassium has similar properties to sodium, it must therefore have similar electron arrangements or configurations, and therefore we're going to make the assumption, and a correct one we believe, that this is where we have some overlap. This is where the beginning of the fourth energy level intrudes or penetrates the outermost regions of the third energy level. So we go with the fourth energy level, S subshell, 1 and 2, and then we see we can now begin to fill up the third energy level, D subshell. So the 4S comes before the 3D. Looking at the periodic table now, you should be able to see that the periodic table predicts that. And again, the periodic table ultimately explains why we have these elements in the arrangement that we have in the periodic table, because it's a reflection of the properties that they have. And in each column, top to bottom, you have elements with similar properties. So we invoke this concept of overlap. The 4S comes next. It's at a lower energy level, if you will, than the 3D. And now we come to the 3D right here. And we go and we begin to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then when we get there, after zinc, we're ready to begin our P subshell. We already have the 4S. According to the periodic table, after the 3D comes the 4P. We already have the 2p and the 3p, so we're ready for the 4p. And you can see we've got 1, 2, 3, 4, 5, 6. That fills up the p subshell. That gives me an inert gas configuration of krypton that looks like this. And we're ready to move to the next row. Meanwhile, you may have noticed something, and that is that right here with chromium and right here with copper, it doesn't follow the numerical sequence. Again, we have 1, 2, 3, and all of a sudden this says for the 3D 5, and then 5 is repeated. 5, 6, 7, 8, and instead of 9, there's a 10, and then 10 is repeated. But you'll also notice that in the 4s, we have a 2, 2, 2, and then it goes to 1. And then down here, we have a 2, 2, 2, 2, and then it goes down to 1. And the reason for that is, evidently, it is more stable to borrow an electron for the s and complete the filling of the d subshell. Or half filling of the d subshell, and borrow an electron from the 4s and complete the filling of the d subshell in copper. So chromium and copper are examples of exceptions to this overall trend. But exception doesn't mean something random is happening. There are always reasons for exceptions, because remember, God's creation is always orderly. There's always logic behind it, even if we don't understand every time what that logic is. And so what we begin to see is that there are other factors in place that determine the structure of an atom as far as its electron arrangement is concerned, besides just trying to fill in the energy levels closest to the nucleus and then using the off-bow principle building out. And that other factor has to do with stability based on thermodynamic principles, which we talked about a little bit in Chapter 5, and we'll talk a lot more about second semester. And so stability rules the day, and things want to be as stable as possible. And it's more stable to have the D subshell filled and the S subshell not filled when you get this close to having the D subshell filled. So you will need to know for your test the exception for chromium and the exception for copper. Now, as you go through the rest of this chart, you're going to see more and more times where there is borrowing from an outer shell to either half fill or entirely fill an inner subshell. So make sure but you don't have to memorize those, because those become more and more frequent and are not as easy to predict. Now, I will say, as far as chromium is concerned down here, if we are doing the block structure for the 3D, okay, and we are putting in our electrons, you would have your 1 arrow, your 2 arrow, your 3 arrow, your 4th arrow for chromium, and you would think this should be 3d4. But it turns out that by adding 1 more electron here and changing that to a 5, and then the 4s, instead of being a 2, becomes a 1, you'll notice now that you have 1 electron in every orbital. And that is indeed more stable than having 1 orbital empty and another orbital with 2 arrows in it. Think about a dorm rooms in a college. Why should you have 2 people in one dorm room and another dorm room completely empty? These 2 people in the dorm room, they have to share the bathroom, share the room, share the desk, share the music in the room, share their toothbrush. Well, I hope not. It's a lot easier if one of these people just says, I'm just going to go over there, and then there won't be any conflict. So that's a kind of an analogy to what we're talking about. Now, there is one other thing I want to point out from this chart. And so I'm going to randomly pick, let's say, the element cerium right here. And please notice that even though the 6s is filled up before the 5d and the 4f, we still write the 4 there, the 5 there, and the 6 there. Now, that's not always true. Sometimes they will write it in the order in which it's filled. So they would have your xenon, and then you'd fill up the 6s2, and then you would have the 5d1, and then you'd have the 4f1. And that would be the order in which you would fill them up using the off-bow principle. And some textbooks will do that on occasion. I prefer doing it this way because even though it does not reflect the order in which they're filled up, we're filling up the 6s2 before the 5d and the 4f, but what it does make possible is the recognition of the fact that if I want to create a cerium ion by removing an electron, let's say I want to create a cerium +2 ion, these are the 2 electrons that are going to be shared with or exchanged with some other element. It's the outermost main energy level. And remember, when you see the word main, we're talking about the biggest whole number, which is in this case a 6. So instead of donating the 1 electron from the F and the 1 electron from the D, it always does it from the outermost main energy level. Now let me point out another common mistake. Let's say I come over here to iodine. The outermost main energy level here, if I'm going to make a iodine ion and gain an electron, let's hold off on that idea for later in the chapter. But if I want to look at iodine, the outermost main energy level is the 5th, and that would include both the 5s and the 5b, because the main refers to the 5. So we would say that iodine has 7 valence electrons in its outermost main energy level. And if we were to do the dot structure, if you remember that from first year chemistry, there's your 2 electrons right here from the S, and then when you do the 5 electrons in the 5p, you would go px, py, pz, the second in the px, the second in the py, and there are your 7 valence electrons for iodine if we were doing dot structures, which of course we haven't quite got to yet. Now, coming over to this page, electron configuration for the main group elements. The main group elements, I'm going to come back over to this chart here, if I can find it. There we go. The main group elements are, I'm going to use a different color, here and here. The main groups are the S and the P. These are the the transition elements. And down here, the F block, are the lanthanides and the actinides. So, electron configuration for main group elements. If we're talking about hydrogen, it's just a 1s1. You can also use a circle and just use a slash. And now you've done the orbital configuration or the box configuration for the hydrogen atom. And you can see it could gain an electron to become a H- ion, or it could lose that electron altogether to become an H+ ion. Now when we come to lithium, element number 3, we have our first energy level, S subshell, 1 orbital, spherical, with 2 electrons, filled. What do we do with the remaining electron, the third one? We put it in the second energy level, S subshell. There's only 1 electron left, so we put it there. If we're doing my blocks, you have that. If we're doing my circles, you have 1, 2 in the 1s, and the third electron in the 2s. Now, we already mentioned the abbreviated form, sometimes called the noble gas configuration or notation, which makes it a lot easier to write out these configurations and saves you time on a test. Unless you were told specifically otherwise, you should always use the noble gas notation. Remember, the core electrons are the ones in there. The valence electrons are the ones outside of the brackets. We come to beryllium. Beryllium now has 4 electrons, and so we fill up the first energy level, And then we go to the second energy level, fill up its first subshell, and you'll notice that the p subshell does not have any electrons in it. Now when we come over to boron, now we're up to having 5 electrons. There are 2 in the first. There are 2 in the S subshell of the second energy level, and only 1 left in the P subshell. Now when we come to carbon, and you could write a book about the element carbon, but the main point I want to make here is that carbon with its 6 electrons, as we do the off-bow principle, we fill up the first energy level, which only has 1 subshell, the S, 1 orbital, spherical, with 2 electrons in opposite spin. Now we move to the second energy level. We fill up the first of our 2 orbitals, the S orbital, which is spherical. Again, it can hold 2 electrons. Now we fill that up. We still have 2 electrons to go. And you might say, well, why don't we do this? Why don't we put 1 electron there, the 5th one, and the 6th one there? And the reason goes back to the dormitory with the empty dorm and the dorm with 2 people in it. This electron goes right there. So sometimes the word you talk about this as sort of being hybridized. We distribute the electrons in each of the orbitals, there and there, whenever there's an empty orbital, because it's much more stable to have a single electron in 2 different orbitals than, like here, to put 2 electrons that naturally repel each other because of their negative charges in the same orbital, even if they have opposite spins. When you have a blank one at the same energy level, you have a blank orbital there, and it's more stable for it to go in there. It's kind of like playing the game Monopoly. When you begin to put houses on a Monopoly, you have to put 1 house on each of the properties in the Monopoly before you can add the second house. And a lot of people don't even follow that rule. They like to put all their houses and then a motel on one property, and the other properties are empty, and that's not according to the rules. Now, this is called Hund's rule. Hund's rule states that the most stable arrangement of electrons is that with the maximum number of unpaired electrons. In other words, it's more stable to have unpaired electrons when you have available orbitals than to pair them up with their mutually repulsive charges and have empty orbitals as well. So that is Hund's rule. You should know that name. And your textbook talks about the exchange energy. There's a little bit less energy involved. In other words, it's more stable. Think about when a house falls down, it loses all of the energy that carpenters and builders put into it in the first place. And so a collapsed house is more stable than a house that is built and standing. That's the same idea here. It is more stable when that energy is distributed in such a way that you have single electrons in available orbitals rather than pairing them up until it's absolutely necessary. So when we look at nitrogen and oxygen, we continue to build. We put 1 in each orbital, and then when we get to oxygen, we start to pair up. We start to put the second house on each property, like in the game of Monopoly. Now, by the way, this would be just as correct if you did this. 1, 2, 3, 4. And in other words, if you're going to be talking about the quantum numbers, and remember with the Z, you have 0 plus, the D, 0 plus 1 minus 1 plus 2 minus 2 to represent the 5 orbitals in the D subshell. This last electron, which is the one they're using to pair it up, you could call that electron, that first, there isn't a D subshell here. We're talking about the P subshell, which is a 0 plus 1 minus 1. This is the D. We're on the P subshell, lowercase p. You can call that first electron that's going into the P subshell. You could designate it a 0 or a plus 1 or a minus 1. You don't have to take it in order of the 0 first, the plus 1 next, or the minus 1 next. That's not required. All right. coming over to here, continue going across the second row. Now we come to fluorine, and in fluorine you can see we now have one orbital left in the p subshell that doesn't have a pair, and as you might expect, it's easier for fluorine to gain an electron than to lose 5 electrons in order to reach stability, in order to reach an inert gas configuration. It just needs one more electron to end up having the configuration of neon. And that becomes important when we talk about bonding. And then finally, when we get to neon, you'll notice that the first energy level is filled, and the 2 orbitals in the second energy level, the 2s and the 2p, are filled. So this is extraordinarily stable, and then it has this configuration, not krypton. It has this configuration here, which would be neon in brackets. Now when we come to period 3, the third row across the periodic table, now we're going to start to fill up the third energy level with the s subshell, and then when we get to the p subshell, again, we begin to distribute the electrons one at a time in each of the orbitals before we go fill it up. By the way, this is something you should know. For general questions on an AP test, the Earth's crust is largely composed of silicon-containing minerals. In fact, there's an awful lot of aluminosilicates, meaning crystalline structures that make up rocks made out of aluminum and silicon. And in my research out in Idaho, I spent hundreds of hours, likely, looking at peaks on my mass spectrogram and trying to discern what combination of aluminum and silicon in a three-dimensional crystalline structure could account for those peaks, because I had to know what the background would look like in order to know what chemicals, if this is a chemical, might be sitting on the dirt. I had to know what the dirt looks like in order to know what the chemicals, what peaks represent the chemicals that might be on the dirt. So this is a good time for you to practice. We will take a look at example 7.2, electron configuration and quantum numbers. Let's tie this together and let's look at aluminum. And so when we think of aluminum, it is element number 13. So there's going to be 13 electrons that have to be distributed. And if you follow along in the periodic table, we're going in the first energy level with the s subshell with its one orbital can hold 2. In the second energy level with its 2 subshells, the 2s and the 2p, so it can hold 2 in the s and up to 6 in the p. And right now you can see that if I add 2 plus 2 plus 6, I'm now up to 10 electrons. So now I need to go to the third energy level for the remaining 3. And this part right here is all neon. So in the third energy level, I fill it up with electrons number 11 and number 12. And now the third electron is going to go in the 3p subshell. So this right here would be the correct way to write the electron configuration for aluminum. Now, when we talk about the quantum numbers, if we're talking about the 2 3s electrons, that's these two right there. One of these, both of them are in the third energy level, so the principal quantum number is 3. Both of them are in the first subshell, which is designated by the letter S, 0. Excuse me, we called it an S, but the quantum number for the S subshell is 0. They are both in the first orbital, and the only orbital in the S subshell, so that has to be a 0 again. The only orbital in the S subshell is therefore designated as 0. It's spherical. And then one of them is going to be the plus 1/2 and the other is going to be a minus 1/2. Now for the 3p electron, which is this one right over here, the 3p electron, it's in the third energy level. You have to have a 3. It's now in the, it is in the second subshell. So that's going to be designated by a 1. And it's going to be in it's going to be in one of the three orbitals, which could be either a 0 or a +1 or a -1. It doesn't matter what you use. And it's either going to be a +1/2 or a -1/2. And you can see that if you're going to use a +1 and either a +1/2 or a -1/2, or you're going to use a 0 and a +1/2 or a -1/2, or you want to use a -1, +1/2, or -1/2, you have a total possible of 6 different ways to write the quantum numbers for the 3p electron. 6 different possible ways, and every one of them would be right. Let's see, I think that covers that pretty thoroughly. So your subshells, you only have, I wanted to clarify I'm sorry, right here. There are only 2 subshells, the S and the P. The S is a 0, and the P is designated by a 1. I wanted to make sure that was clear. Now we come to the transition elements, and when we look at the transition elements, we're looking at the D subshell, and then you have your inner transition elements, because we're going to stick them up. Notice, folks, right here, I'm going to blow this up, that they are put into there, and they're not inserted there. So in other words, you put 1 electron in the 5D and the 6D. Remember, this is the 3D, the 4D, the 5D, the 6D. You're going to put 1 electron in the 5D before you come down here and do the 4F. Remember, there is no such thing as a 1, 2, or 3F. And down here, when you get this many electrons, you're going to put 1 electron in the 6D before you come down here and start filling up the 5F. That's what we observe. Creation is pretty complicated. Now, I would strongly recommend, and we may do this in class, that you watch this video, which actually shows using 3-dimensional animation in a 2-dimensional platform, of course, what all these orbitals on orbitals on orbitals look like. In other words, when you get all the way to scandium, which is element 21, what is it going to look like when you have 4 S subshells, 1s, 2s, 3s, and 4s? What's it going to look like when you have several P subshells, the 2p and the 3p, all on top of each other in the same region of space with the scandium nucleus in the middle? This is an excellent video to show that. Also, here is where I talked about chromium as the exception and copper as the exception, where they borrow an electron from the 4s in order to half fill the 3D, because that's going to be very stable, to be like this, where you put 1, 2, 3, 4, 5, that's very stable. And then down here, you're going to have all of them filled up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are many more exceptions in the 5th and beyond, which you don't have to memorize. And then I also mentioned the idea that we stick 1 in the 5D before we start filling up the 4F. So we fill up the 6 S first, and then after that, we're going to start to fill up the 5D, but with just 1 electron, and then immediately we go to the 4F, and we're going to go 1 through 14 in the 4F before we go back to resume filling up the 5D. So make sure you remember that. And finally, this all relates back to the idea of Z star. And this is the apparent charge that an electron is going to experience from the nucleus. And that is because that you have all those core electrons that are between the valence electron and the nucleus. And they shield the valence electron from the central charge. So whatever the number of protons are in the nucleus, not all of that charge, in a sense, makes it out to the valence electron. A lot of that charge, so to speak, is used up holding the core electrons in place. So the full magnitude of all the protons in the nucleus is not experienced by the valence electron. That's where we have the term shielding here, okay? And that's where we have the term the effective charge that the valence electron experiences is represented by Z star. And you can see these trends. And because the amount of energy that the valence electrons experiences goes down, the amount of positive pull, protonic pull, so to speak, that the valence electron is feeling from that central nucleus goes down, the size is going to shrink as you go from left to right across the periodic table. And here again, I would suggest you do these two as practice and see if you can come up with those answers. And if you have any questions, let me know.